you had a hand up, Laura?
Oh yeah, I was wanted to ask about graphene and was wondering where you see the field going and when you think the hype, the point of the hype will be reached and when it's going to go downhill from.
We may have maxed out on the hype already, possibly. I mean, I think it's going to be very interesting to see where graphene goes. I think there's going to be a lot of work. There's going to be a lot of engineering work done because there's reasons why graphene could be a really interesting material from the standpoint of actual devices. Though again, even that's a ways off. I think some of the stuff in the Nobel citation is rather optimistic. The description of how soon it's going to be generally useful. But I mean, the one thing I will say about graphene, I don't know of a single experiment that's been done in graphene where people can't really pretty much explain the answer. And so that's usually not a good sign for a longevity of the field as a piece of physics. Like, it could be a great piece of engineering. But I mean, the example, you may have a different opinion on this, but the example I would give is there was a, again, there was a compound called magnesium diboride, MgB2. Amazingly, people missed this in the 60s somehow when they were basically examining every binary compound for superconductivity. Magnesium diboride, it was discovered in around 2001, I think, has a TC, it goes superconducting, and the TC is 39. And it's really just an extreme version of a conventional superconductor, we now know. But it was a huge surprise. And again, if your metric is March meeting talks, I mean, there was an enormous explosion of interest in magnesium diboride, sort of like pnictides in the sense that, wow, here's a material, what on earth is going on here? Well, the problem was, it had really just been overlooked. Nothing super exotic was going on there, and pretty much the whole field of magnesium diboride was done to completion in about 18 months. Like, people knew pretty much everything there was to know about the material, unless you want to do engineering problems and actually try to make it into wires and wine magnets and things like that. I mean, it's got a lot of very useful properties, but so it kind of, when there are no surprises in the experiments, it makes you think that maybe we actually are going to, maybe we're going to know everything that's important to know pretty quickly.
And another question that we have is, what areas of condensed matter do you hope to see people work on more in the future?
Okay, well, it's somehow related to the, somewhat related to the hot topic question, right?
Yeah.
Well, let me just point out that out of the hot topics that we mentioned here, which were the topological insulators, the iron pnictides, and the graphene, all three of them have appeared after 2005, after I've done my PhD. So it's just interesting how, so if this is anything to go by, either there was an explosion around 2005 of new stuff, or the half-life of these discoveries tends to be short and the interest of the public tends to shift. I'm not sure which of the two. But if you're a pessimist, then you would say that in 5 years from now, probably not many people would talk about topological insulators or graphene, or maybe even pnictides anymore. Or maybe they will. It depends sometimes on the politics, policy-making issues, and the nature of funding. So I personally would like more people to work on more interesting stuff as opposed to more hot topics. And what I mean by more interesting is something that would be not necessarily that the problem has to be dull. It's more that the problem has to have intrinsic interest in it. Not because, let's say, TC is higher than a certain temperature range, but because of something that was not understood or isn't understood draws the attention to it.
Yeah, I agree. I mean, I think, so condensed matter, it's a strange thing, right? On the one hand, it's probably the field of physics that has affected your life more than anything else, directly speaking. On the flip side, it's also something that I think too often tends to get wrapped up into, so is this going to lead to faster computers? I mean, there are really pretty profound, pretty deep issues that show up in condensed matter physics that I kind of wish more people thought about or worked on. I mean, I would say if I had to name a general area, I mean, I think systems out of equilibrium and how do, if I take a system and I drive it out of equilibrium and I just let it sit, so I apply some voltage across something and I let current flow and eventually I reach some kind of a steady state. Like, how does that work? I mean, how does the steady state arise? Where are the irreversible things happening? I mean, what are the origins of irreversibility? I mean, condensed matter physics has had lots of interesting insights that have carried over into high energy physics about things like broken symmetries and symmetry breaking and the role of symmetry. And I think there's a lot more in there. There's a lot of really interesting stuff in sort of the more fundamental side of condensed matter that can now be probed with experiments. And I think some of that may have more longevity than the latest material that someone happens to have discovered.
I think we should wrap up. Let's give them a round of applause. And if you haven't already, please sign the sign-in sheet that came around late. Sorry about that. And take some sandwiches. Eat them.